I'm Don Mackintosh. We're glad that you've joined us for this special presentation by Drs. Bob and David Gentry, and we're going to take a closer look at that presentation. We're in the studio with Dr. Gentry right now. We're going to talk a little bit about the presentation, hopefully looking a little more in depth so we can understand more fully what we've just heard, and hopefully I'm going to represent you and ask some questions that you would have asked if you were sitting where I am. So first of all, thank you, Dr. Gentry, and also thank you to David for being involved in the presentation of this thought-provoking material.
Don, you know that it is thought-provoking from the standpoint that, for example, years ago I was an evolutionist myself, and I was out telling people all the good things about the Big Bang and the ancient age of the Earth and the fossils. But one day came and I was reading the Bible, and all of a sudden I read this fourth commandment there in the Bible, which you're very, very, very well familiar with. And it said, "For in 6 days the Lord made heaven and earth, the sea, and all that in them is, and rested the seventh day." Well, prior to this time, as I said, I'd been an evolutionist. I had equated the 6 days of Genesis with 6 long cosmic periods of time. But here in the fourth commandment, it said, 6 days, seventh day. I knew the seventh day had to be 24 hours, and I couldn't believe that indeed, in that one sentence, the days of creation, the 6 days, had been translated from being 24 hours, to cosmic periods. So that really caused a lot of problems, and I began to search for a reason and understanding of how I could reconcile my science with, this new understanding of the Bible and Genesis. And so it caused a real problem. I couldn't find anyone that would help me to understand it, Don.
Well, that tension between those two, I guess it took you some time to work through that, a number of years, as I understand. And now you've taken a position, and you and David have some real solid scientific thinking behind it. Explain how that all came about.
Well, my wife and I, and becoming, believers in the Bible, the literal creation narrative, as we see there in Genesis, repeated there in the fourth commandment, we just couldn't find anyone that would give us a satisfactory scientific explanation that would overturn my long-standing scientific presumed explanation of the universe. Billions of years, the Big Bang, billions of years for the cosmic geologic evolution of the Earth. And so my wife and I went back to the University of Florida. I was teaching there for a while, and she was working on her degree in mathematics, and she came home and she said, "Listen, I'm taking the same biology course you took many years ago, and the professor is standing up there and saying, if anyone believes in Adam and Eve and the 6 days of creation, they're just far out." In other words, being very, very critical of anyone who took a literal perspective on the Genesis record of creation, and she saw that there were students there who basically were being really criticized. They were losing their faith. And so she said, we just can't go on like this. We believing the Bible one time, and you're in this business of believing the ancient age of the earth or whatever you used to believe. And she said, "Isn't there something we can do?" And so
that caused you to start studying. Your wife really put the laser beam on you and said, "Let's really figure this out."
Well, that's true. It had been an ongoing quest of mine to try to find out, understand what's going on, but that really did trigger the situation. There's no question about that. And so here, just about a year or so later, I kept on then trying to delve into the situation. We went and I began teaching at a small college up in Washington State, and the issue there became more and more focused. Then I said, I've got to get a PhD in physics because I need to find out more, and I need to be not just with a master's degree in physics. I need to be able to talk to the scientific community from the standpoint of someone who has this degree, this PhD, so someone will listen to me, whatever I might find. So I applied and obtained a teaching position at Georgia Institute of Technology and began to teach and also work on my PhD at that time. But I also then went to the department chairman and I said, I've got the perfect idea for a thesis, PhD thesis. And he said, "What is that?" And I said, "What's the age of the earth?" And he looked at me and he said, "Age of the earth?" I said, "Sure, I'm in a situation where I'm trying to resolve in my mind what's going on, because when I grew up, I believed in the biblical record of creation, 6 days, didn't have any question, went to the university and took biology, and then I took physics, graduate physics. I learned about the Big Bang, I learned about geologic evolution, and I thought, you know, I have learned the truth. And yet here I find, in rereading the Bible, here's this fourth commandment and those 6 days of creation, and I said, something is wrong. I don't know what it is, but I can't necessarily believe the Bible.
One is right, one is wrong. You got to figure out which. Now, was he overjoyed when you said, I want to do something on the age of the earth?
Actually, no. He said, you know, he used to be a fervent 6-day creationist himself, and that in going to university, he became a physicist, and in evaluating and weighing all the evidence, he said, listen, you know, there's no reason for me to fight against the scientific community. This thing must be true. Evolution must be true. The Big Bang must be true. Geologic evolution must be true. And he said, so for that reason, you know, I feel you'd just be better off to forget about this whole idea. Well, we left. I mean, I was eating with him one day, and when he said that, then I ate with him again. You know, he said, come and eat with me at lunch. And so we did it again. Then we did it again. Then we did it again. And every time we met, that was the topic. And he said, now listen, here's the situation. You're here at Georgia Tech, and you're teaching. And, you know, you're going to get a PhD if you just stay continuing to take the courses and everything. But I tell you what, this business of the young age of the earth as your thesis is just not going to work. You just got to make up your mind it's not going to work. And I said, well, you know, I really do need to know the answer. I said, all right, here's the alternative. He said, I don't think you have a microscopic chance of finding anything if you were to delve into this topic. However, even though I don't think there's any chance in the world for you to do anything or find anything, what would happen indeed if you did? You're here at Georgia Tech. You're a faculty member. You would want to publish whatever you would find. And he said, if you were to publish something that would really even question the theory of evolution, he said, this institution, it would just go up in smoke, so to speak, you know, in opposition. He said, absolutely cannot afford that microscopic chance that you might find something. And so he said...
That doesn't sound like a real open, scientific, inquiring mind.
I tell you what, we're going to find out. As I continued to progress in doing this, I found out that there are certain things that are off limits. They're not only out of the box, but you're not allowed to investigate because the ramifications of what you might find. Anyway, he said, you know, if you really want to continue this, you better find some other place to go. Stay here. I'll give you a thesis topic you can do. All will be well. But if you want to do this other, he said, you're going to have to leave.
And so you left.
So I left.
And you were in pursuit of truth concerning not only the beginning or, you know, creation's tiny mystery, the book you've written, looking at documenting how that all happened in a rapid fashion as the biblical account also describes, but also then looking at cosmology, this Big Bang theory. And you're going to tell us a little bit about that, about why that's wrong.
Well, that's the purpose of us getting together today, to explore this in greater detail so that those who have watched the video will have a better handle on exactly why and so forth that's wrong in this new model of the universe of all things. Just going to give you a little more background. See, when I was taking physics, and this I think has happened to just about everyone, when I was taking physics, you know, you go into the laboratory, you do experiments.
Right.
Laws then are determined, and those laws are tested over and over again. The fundamental premises of Newton's second law, of all Newton's laws, of Maxwell's equations, of electromagnetic theory, all these have been verified over and over and over again. But what happened when I was taking the courses in physics, that in addition to that, those are factual. But in addition to that, then the theory comes in about the past.
Origins and cosmology, all those theories.
That's right. Now, what most people don't understand, and what I didn't understand as I was going through, is that the theories about the past rest on assumptions, and I found out much, much later that had never been tested. They didn't tell me that when I was going through, so I assimilated the idea that the theories of Big Bang and geologic evolution, ancient age of the earth, and so forth, were just as valid as Newton's laws of motion.
I see.
And so I didn't have any idea. No one ever told me to think about it. No one ever taught it. I don't think they even thought about it. They just said, you know, people in the past have found this is true, and so therefore be a good boy, learn it along with the laws of physics, and all is going to be well.
And you didn't settle for that. You said, I want to look a little closer, and what you discovered is really what we've just seen in the presentation you made, but we want to amplify that now.
Yes, because many, of course, in looking at what we have just seen, David and I presented, and of course you, does challenge very seriously the conventional viewpoint of the origin of the universe, the origin of the earth, and where we all came from. And not only that, one of the things that was driving me in doing all of this is that I had an inherent belief that God was actually telling the truth. I could not believe he would present one story of creation in the Bible and another story of creation in nature so vastly different. So it was in a search not only for the truth about creation, but it just could not believe that the Bible was written for, I understood later, or even at that time, for the person who was not a scientist to be able to read. And you didn't have to be supposedly a physicist or a cosmologist or an astronomer or a geologist to be able to put it in the framework of common life. And so it was a search, began a search for this, what I felt must be, but I didn't know for sure, was going to be a correspondence between the science that I didn't know at that time and, of course, the Bible, the Creator himself telling us the truth about ourselves and about the history and about Jesus Christ and about salvation.
I mean, for many scientists, it's just a taboo subject to try and bring in any other authority instead of what is observable by science. And so naturally, someone who's a scientist tries to be completely, totally objective, but a Christian who is also a scientist, or a believer who is also a scientist, has those two sources of authority, and both of them are valid, and one of them, of course, has been around a long time. So you're going to lead us through that. This presentation was focusing mostly on the Big Bang Theory and looking at a completely different take on the data. The data is the same, but the conclusions are different.
Let me just say one thing about one part of what you said. The general consensus in the world is scientists are honest, open-minded. If they see anything that challenges the conventional viewpoint of anything, any theory, they're all going to jump in and check it out and so forth. The fact of the matter is that scientists are human beings, and they have agendas. They have philosophical viewpoints, and the fact of the matter is, as we're going to see in more detail here in a few minutes, that they have not been, absolutely have not been open to rethinking their fundamental postulates and looking at them to see what might be there in terms of a different viewpoint as it pertains to creation itself. So let's start then by, I want to go to a statement by Steven Weinberg, Nobel laureate in physics, as he talks about the way in which scientists then begin to look at the universe. A quotation from his book, The First 3 Minutes. In the following, this account of the first 3 minutes, the reader may feel he can detect a note of scientific overconfidence. He might be right. However, I do not believe that scientific progress is always best advanced by keeping an altogether open mind. It is often necessary to forget one's doubts and to follow the consequences of one's assumptions wherever they may lead. Well, nevertheless, there is one great uncertainty that hangs like a dark cloud over the standard model of the Big Bang. Underlying all the calculations described in this chapter is the cosmological principle, the assumption that the universe is homogeneous and isotropic. The great thing is not to be free of theoretical prejudices, but to have the right theoretical prejudices. And always, the test of any theoretical preconception is in where it leads. The standard model of the early universe has scored some successes, and it provides a coherent theoretical framework for the future experimental programs. This does not mean that it is true, but it does mean that it deserves to be taken seriously. He's saying underlying all the calculations in the Big Bang is this so-called cosmological principle. And the words homogeneous and isotropic that you see there is just another way of saying they assume the universe is everywhere the same. Well, why would they do that?
Well, you know, I mean, the statement itself is kind of contorted because it says we're going to be honest, but we're not going to be honest. It's going to be true, but it's not really true. But let's go with it.
let's have a quote, the right theoretical
So
prejudice.
who is Weinberg, just for my information?
Professor Stephen Weinberg, University of Texas, is probably one of the 10 best theoretical physicists in the world. He's a Nobel laureate, greatly respected throughout the scientific community. And you see, he's saying here, we've got to have the right theoretical prejudices. And there's a reason why he keeps saying things like that. And that is, of course, that it is this assumption, but you notice it says cosmological principle.
What's that mean?
That's an ingenious
way
of saying something that it really is not true, but you're going to make it a principle. In other words, there are principles of gravity, principles of electricity and magnetism. It's one of the things we talked about a little bit earlier. I talked about meaning that they're going to elevate something that is an assumption to the standpoint of a principle. And so the man on the street, he hears about the cosmological principle, and he said, well, you know, they got it made. They really know where we came from.
But they don't know.
And the man on the street doesn't even know how to ask the right questions because they've disguised it all so badly.
Okay.
Then let's go to something else here. We're going to go to the book on Cosmology by Edwin Harrison. And we're going to go there because look what it says about the Big Bang.
Okay, let's look at it.
Science clings tenaciously to the concepts of conservation, the most fundamental of which is the conservation of energy principle. The conservation of energy principle serves us well in all sciences except cosmology.
Why not?
Whoa.
Why?
We're in the universe, and the Big Bang envelops the universe, and so basically he's saying it's going to serve us in all sciences except cosmology. Well, we're part of the universe. We're part of the Big Bang, supposedly.
Right.
To the question where the energy goes in an expanding universe and where it comes from in a collapsing universe, the answer is nowhere, because in this one case, energy is not conserved.
So everywhere it's conserved, but not here. And the question is, why in the world would someone say that? That seems totally inconsistent.
Well, this text that we just saw, a cosmology text, is widely used in universities all across America for 2 decades. And students then have read this, you know, yes, we need to conserve energy in physics, but in Big Bang we don't. But the fact of the matter is, supposedly, in their view, Big Bang governs the universe. So how can you have non-conservation of energy in a universe where all the tests and experimental tests in physics say energy is conserved? Big contradiction. But you see, it just goes in and out of the minds of other astronomers, and they don't say anything about it.
So this is one of your big problems with the Big Bang theory. It is going against this prime law of physics, which is conservation.
Well, that's true. In fact, you see, one of the fundamental premises of all of science is, you know, like electricity and magnetism, about Newton's 3 laws, that you have certain basic postulates upon which those laws and electromagnetic theory are based. You go to the laboratory and you verify those postulates, and then you go and say, okay, we'll use them, it works. Now, what they're basically saying here in terms of this non-conservation of energy, a basic law of all physical theories is you've got to verify the fundamental premise of the theory before you go any further. Well, in this case, if you find then a violation, if you find a falsification, if you find a contradiction in the fundamental postulate or principle of any theory, the whole thing is down the drain. And here's the point. You're very well familiar, of course, with the fact that Ptolemy, several thousand years ago, devised this theory of planetary motion. In other words, you look at the sky, you see the planets and so forth. He had a very ingenious plan, and it worked very, very well. Everything was rotating, revolving around the Earth as the center. Then you put the galaxies, you put the planets out there, and they rotate themselves about something else. Anyway, it worked for 1,000, 2,000 years, and everyone believed in it. But what do we find? Copernicus comes along, and he looks at the cosmos, he looks at the solar system, and he says, wait a minute, that's really not the case at all. That really what is happening, going back to the observations Tycho Brahe and others, that what is really happening is that there is the sun, and the sun isn't going around. Everything is going around the sun. Whoa, lights come on. But I tell you what, there was tremendous opposition to this.
Yeah, the
tremendous
church
opposition. So anyway, the point is that a theory can be accepted for thousands of years, and it can explain a lot of information, not everything. There were exceptions to the Ptolemaic theory that could not be explained, and they had to keep adding on, adding on, adding on to try to get it to work. But the problem is, the truth is that when Copernicus found out the truth, then, you know, no matter what people did after that, they found out that they had been relying on belief in a theory because of the amount of data that the theory could explain. And that's exactly, we'll find, is what's happened there in the Big Bang.
So
We got this tremendous contradiction, and a sophomore in college who's taking physics should be able to read that and say, well, wait a minute, something has got to be wrong with Big Bang because it violates conservation of energy. Yet no one picked up on it.
well, let's go deeper then. I mean, that's a major part of the presentation you've made. But let's look. If the Big Bang Theory then violates that, you know, why do scientists believe it? I mean, that's the question we've asked.
Right. Well, the 20th century provided us with two huge astronomical discoveries. One, the discovery in 1929 by Edwin Hubble, the redshift relation, which we'll talk a little bit more about. And then in 1965, the so-called cosmic blackbody radiation. It was so important a discovery that NASA built a satellite, put it up in the early 1990s, and it was revolving and revolving around the Earth. And basically what they found, what Penzias and Wilson found back in 1965, was that there is this invisible radiation. They found it with a radio antenna, which we can't see, of course. They weren't looking for it. But in building this radio antenna to look for something else, they noticed what they said was noise in this radio antenna, and they looked and looked and looked, and they couldn't find any reason for the noise, and they kept turning the antenna one way or the other.
It was just everywhere in the universe.
It was coming from every direction they pointed this radio antenna.
Okay.
Well, what does it all do to? And they were puzzling and puzzling and puzzling. How can you explain this? And they were at Bell Labs, Homedale, New Jersey.
Okay.
Not too far away at Princeton University. There were a couple of scientists there, Robert Dickey among one of them. And they were thinking, well, you know, this thing called the Big Bang. It went off a long time ago, but as we'll find a little bit later on, the theory of the Big Bang, the fundamental premise of the Big Bang is that radiation, light, wavelengths expand as supposedly the universe expands. And so basically they said, what we believe then is that the Big Bang went off, there was a fireball, and for no other reason than the expansion of space itself, the light photons, the light wavelengths of all that radiation began to expand, 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 which means, of course, you get redder and redder and redder. So something that was as bright as the sun, the radiation coming from the sun, well, after a period of time, supposedly, that radiation would get dimmer and dimmer and dimmer, redder and redder, and then finally it would shift to the microwave region. And so they said, aha, they found out. In other words, they heard about the discovery of Wilson and Penzias, and so they immediately contacted them and said, we believe you have found the golden grail of Big Bang cosmology. That is, this supposed relic radiation from the Big Bang itself. And so when Penzias and Wilson published their paper of discovery of this radiation, then Dickey and someone else actually wrote a paper and said, we think this is the reason why you're finding this. It's the golden grail, proves, so to speak, if this is really true, we got the Big Bang nailed. And so
in other
those
words,
two reasons.
this idea that radiation was everywhere was taken as by them as proof that the Big Bang is true.
Yes. Well, proof too strong a word to begin with, but then scientists around the world, astronomers, astrophysicists said, we really got to find out if this is true, because if this really is cosmic blackbody radiation, there's only one explanation, and that is it's got to be from the Big Bang. And sure enough, as more and more measurements were made, remember this was 1965, 1990, or thereabouts, NASA sent up this COBE, Cosmic Orbiting Background Explorer satellite, to measure this radiation more precisely. And what they found was indeed it has what is called a black body spectrum. And that's what you're looking there on the screen.
Okay, so that black body spectrum, I mean...
Bell-type spectrum. That's right.
Okay.
What does it all mean?
Yeah.
Well, has scientists ever seen anything like this, seen this spectrum before? And the answer is yes. For over 100 years or more, they in the laboratory recognized that if you have an enclosure, suppose you have a shell or a box or whatever, and you heat it up to, you know, red hot or whatever, and you put a little hole in it, and then you just measure the radiation coming out of that little tiny hole, then the spectrum of the radiation, by radiation we're meaning something like light, except it's in a different part of the frequency spectrum. We can't see radio waves, we know that. We can't see the microwave.
But they're there, and it's measuring that.
But we can see light, but we can't see, if you go further up in frequency, we can't see X-rays, we can't see the gamma rays, but in this limited region that we can see the visual part of the spectrum, we can see it. But anyway, they measured this spectrum of what's in the enclosure, the radiation in this enclosure. It always had that sort of bell-like spectrum, no matter what the temperature was. So when they finally saw this spectrum, they said, we've got it made, because you see, if you don't have anything in the universe, and you have the Big Bang, and it begins to cool down, nothing, the radiation is not interacting with anything else, begins to cool down, it's going to cool down, like they said, they suppose, a black body. In other words, we're inside, supposedly, a black body. And so that, you know, it was worldwide news in physics, newspapers, and so forth, that indeed this really, really, really was the answer to everything in terms of the Big Bang. And it turns out that Penzias and Wilson got the Nobel Prize for the discovery of this cosmic black-body radiation.
So you're trying to take it away from them. You're saying, hey, that's okay for your smaller experiment, but to expand it further is, for some reason, not valid.
Okay, let's make sure that we may go over that just one more time. In the laboratory, you can always go, if you have an enclosure, an oven of some kind, no matter what the radiation temperature is, temperature of the outer box or outer shell itself is, if you poke a little hole in the enclosure and then measure the spectrum, then you're always going to get something like this bell curve. Now, if indeed it's hotter and hotter and hotter, then the spectrum is going to shift to higher and higher frequencies.
Okay.
If indeed the enclosure has a lower temperature on the outside, it's going to shift to longer and longer wavelengths. So when they saw this, they said, this has got to be a black body. It is a black body spectrum, because we can see that in the laboratory. The question is, what is the origin of this black body radiation? And they jumped immediately, as I said, with the idea that it's the relic radiation from the Big Bang. Now, in the meantime, since 1965, thousands, tens of thousands, probably at least 100,000 or 200 or 300,000 scientists have searched for another explanation for that cosmic black body radiation.
Have they found anything?
That's what we're going to talk about.
Okay.
And the answer to what they have found, or have they found anything else? Answer is no. And so this is why the Big Bang has just grown over, has grown and grown and grown in presumed scientific validity. That's why it's so difficult for them to consider the possibility, after they've gone out on a limb, supposing, and said it's all true, consider something else, another explanation.
It's going to be some serious egg on the face, so to speak, if there's another explanation. And that's what you're positing here.
Well, we want to make sure that we understand that the reason we're challenging this and saying there is another explanation is because if you look carefully just at the evidence that they know about
itself, right,
then they should have looked a lot further before they're making these great proclamations. Now, this is taken from a report by Victor Weisskopf. Now, Weisskopf is a very, very well-known scientist, and he's writing in American Scientist about this cosmic black body radiation. Now, the reason he's writing about it is because he's admitting that it is a reference frame for the universe. But guess what? General relativity, according to Einstein, says there is no fundamental, primary, absolute reference frame for the universe. And so let's look at what Weisskopf is saying. It is remarkable that we now are justified in talking about absolute motion, and that we can measure it. The great dream of Michelson and Morley is realized. They wanted to measure the absolute motion of the Earth by measuring the velocity of light in different directions. According to Einstein, however, this velocity is always the same. But the 3K radiation, that's the black body radiation, represents a fixed system of coordinates. It makes sense to say that an observer is at rest in an absolute sense when the 3K radiation appears to have the same frequencies in all directions. Now 3K represents 3 Kelvin, almost down to absolute zero. But basically what he is saying here is, you know, there's something here that is contrary basically to what Einstein, you know, presumed. But here it is. Now let's see what else he says. Nature has provided an absolute reference frame. The deeper significance of this concept is not yet clear. Lights go on in my mind because Psalm 103:19 says that indeed thy throne, O Lord, is fixed in the heavens. Thy kingdom rules over all. In other words, here in the Bible we have a distinct reference to a fixed point, meaning the throne of God. It's not wandering throughout the universe, it is fixed. And so what I'm saying is that if you read the Bible, and it began to occur to me, not initially of course, but as I began to continue to study, I found that verse in Psalm 103:19, and I said, wait a minute, now I know why Victor Weisskopf is puzzled. He doesn't understand how to put an absolute reference frame in the universe because why? Einstein said it doesn't exist. But the Creator said it does exist long before Einstein, and he has actually provided this absolute reference frame. So what we're saying is, one thing for sure, in my opinion, that the Lord put this cosmic black body radiation in the universe is to show indeed there's an absolute reference frame, connecting the Bible statement, his throne, with the fact that it is immovable. I like to bring out one other point here in that context. So, if you had a question.
So, first of all, what we've said is, or what you've said is, that the Big Bang theory is suspect because it goes against the prime law of conservation.
That's right.
Secondly, which usually in physics, if I'm understanding correctly, we try and conserve energy, but this goes against that, and they say, well, who cares? This is a truth in cosmology, but nowhere else. But they have no way of really proving that, but they say that. Then secondly, this black body radiation that's everywhere is a problem, and this particular person is honest enough, this scientist, to say that is a problem because it makes us begin to entertain an idea as a scientist that there might be some kind of absolute reference point. But what do I do? Because Einstein says that can't be, and other people say that can't be. Is that what you're saying?
Absolutely. That in itself was not as significant in terms of shaking the faith of any scientist, the second point here, as the non-conservation of energy. Well, in fact, you know, if non-conservation of energy doesn't shake the faith of a scientist, then
probably
what is going to do that? And so, but it is significant, very significant, that we've had these 2 points thus far.
Now, before you look more at, you know, you've suggested a Bible text, and for a scientist, I mean, that's probably, for most scientists, and you're a scientist, so I don't want to lump you together, you're different in this sense, but for most scientists, they say, what are you doing bringing that into this? Is there any other evidence that you would want to bring out, you know, before going to that other source of authority, that being the Bible?
Well, of course, we've got a lot more to say, but while I was bringing this out, you see, these are the 2 main crutches, so to speak, the 2 main supports of the Big Bang, and so even
conservation and black body
that's right.
Radiation, okay.
And of course, there are some other things connected with this black body we're going to find out in a few minutes that make it essential, this black body radiation make it essential to an understanding, or at least the premises of Big Bang itself. The question is, see, we observed the black body radiation. The question is, what is the true interpretation
of the data,
of the radiation itself? And the radiation, the interpretation of the radiation depends upon the fundamental postulate of the Big Bang, which is this space-time expansion. That's what we're going to get into.
Okay. Are we ready to get into that then?
All right.
Let's do it.
Now, the first, remember, we said the first big crutch of the Big Bang was Hubble's discovery way back in 1929, and it presented cosmologists with a huge, huge, huge problem at that particular time, because they were accustomed to actually looking at the data from the standpoint of the Doppler effect. But before we get to the Doppler effect, let's see what the universe is all about. And this is what we saw, of course, in the early part of the first video.
Okay.
Here we have the Hubble Space Telescope, which NASA has very, very kindly manufactured, sent it up there to orbit, and so now we can see things in the universe that we never were able to see before. And remember, in this previous video, we saw the Eskimo Nebula.
All these wonders of the galaxy.
And here, of course, is the Ant Nebula, and we made a comment to the effect, implied, of course, that these things are supposedly the result of just chance, because the Big Bang starts by chance, it proceeds by chance, and so forth. So everything we were talking about in the earlier part of the first video is everything. If you believe the Big Bang, all this that we're seeing here, these pictures, all just a matter of chance. Cat's Eye Nebula, and then the Barred Spiral. Now remember, we said that the center portion there probably had a couple of 100 billion stars, and then another 100 billion stars or so in the actual arms themselves. Then we have Hoag's Ring Galaxy. We're pointing out, of course, essentially that there's more geometric representation here in the universe than you can begin to imagine, you know, just by chance. That's what we're bringing out, of course, here and showing these galaxies. And here, of course, are the mice galaxies, meaning the way in which they are viewed there, 300 million light years away from us. Someone, in my opinion, you know, is trying to attract our attention.
So when you look at all these things, you show all these wonders and beauties of the galaxy, you're saying they're too geometric, they're too beautiful, they're too elegant to be something that's just chance. They're something that point us to something else other than random occurrences.
Well, that's true. But let's also remember, earlier, what we're saying today, we quoted the book from Trefl. And Trefl said, you know, we've tried to go and we've tried to understand, we've tried to get models of how the galaxies formed, and over and over and over again we try, and everything we try basically comes to naught. Now, you ask the question, you may ask the question, or it may come to your mind, why is this I read all the time, you know, about the astronomers knowing how the galaxies formed here and the galaxies formed there, and on and on and on.
Stars being born,
That's
this and that,
right.
all these different things, they seem to be able to explain why what you see is happening.
That's right. Now, is not the implication of their saying that the fact that they can actually see something like that happening?
That's what you would believe. I mean, sometimes I've heard or read where they say, hey, look, there's a picture of a star being born.
Have you ever seen a video clip of the development of a star from supposedly an embryonic stage to really being a star?
I never have seen that.
You know why you
I
haven't
wouldn't
seen it?
purport to be someone that has watched all those things, but I've never have seen it.
Well, the fact of the matter is it does not exist.
Okay.
What you're seeing is a snapshot. Absolutely. Even they admit it.
And then the other things that are built on top of that are assumptions that they make, and they come across as purporting to be actual occurrences.
Well, absolutely. In other words, they're taking snapshots of the universe. You know, they have galaxies there, say, you know, this is a blue galaxy, therefore there are lots and lots of stars being born in this blue galaxy. You see another galaxy in there, it's red, well, this is a dying galaxy. You see another galaxy, it's got some other features in it, and this is all a part of the, they say, the evolution of the universe. In other words, they take the observations and they move them over here to the framework of the Big Bang. Underlying it all are these assumptions that indeed, you know, the Big Bang is really the truth about the universe, and indeed, it's put out to the world, and people say, wow, isn't this wonderful, you know, the universe is so old. And there are a lot of people, there are some people here in recent years that have begun to promote the Big Bang and say, you know, this is the way that God created over billions and billions of years. What do they say? They say, well, God did it over billions of years, and we can easily equate then what? The 6 days of Genesis with 6 long cosmic periods of time. No problem. Forget about, you know, the 6 days of creation being literal. Behind it all, for those individuals who are presumed to be believers in the Bible, they have an agenda. They, in many cases, in fact, books are written where they want to get rid of that.
Yeah, and that in your first, you know, book and one of your first presentations now on DVD was that by looking at the granites, that's wrong. And now looking at the cosmos, you're saying that's wrong too, because the data itself doesn't match up.
That's right. And in other words, in the cosmos with astronomy, you're taking snapshots of, you know, basically the universe. You're not seeing anything, quote, develop.
Right.
This is an interpretation. Okay, with respect to the Earth, you just mentioned the granites. Here on the Earth, you know, with respect to the origin of the granite, supposedly over billions of years, slowly cooling Earth and on and on and on. The fact of the matter is, again, the basic premise there is supposedly granites formed deep underground, but nobody has ever seen it. And so they put an interpretation. It's all a result of a slowly cooling Earth.
What's the next step they
all right, you know, this other beautiful starburst galaxy there, and then we have this fantastic number of galaxies in the universe. Here it is. The problem of explaining the existence of the galaxies has proved to be one of the thorniest in cosmology. By all rights, they just shouldn't be there. Yet there they sit. It's hard to convey the depth of frustration that this simple fact induces among scientists. Time after time, new developments have come along, and it has seemed the problem was solved. Each time the solution turned soft, new problems developed, and we were right back where we started. Okay, so basically we're saying here that, you know...
A problem, he's saying there's a problem when we see all these galaxies there. He's saying, look, I mean, this doesn't make sense with the other stuff we're presenting. Well, what's the problem with seeing the galaxies there for him?
Well, basically they're saying they don't even have a good model that it can be validated. They got all sorts of assumptions that go into. You can sit down at a computer and, you know, basically engineer some assumptions to go with, you know, a computer animation, and you can produce galaxies, obviously, with the computer and with certain assumptions. What he's basically saying is they don't have any real basic fundamental assumptions that can explain the formation of the galaxies, but very, very few people will admit what he is admitting right there.
Okay, so he's admitting big problem with existing Big Bang Theory, all kinds of problems with it, but not too many scientists even admit that.
Absolutely.
And you're building now on this admittal to look at the data a different way.
That's right. So let's take a look at Hubble. Of course, there he is. Now, Wilson telescope, looking through it back in the 1920s, and he comes up with the fact that indeed the light from the galaxies is actually shifted to the red end. And this is a very common
You believe
phenomenon.
that?
Well, as a physicist, I have to believe it because I can go in the laboratory and actually move a sample away from a spectrometer, and you can actually see the lines, the spectral lines actually move. And the policeman can actually uses that. He uses microwave, of course, shoots, you know, the beam at a car. If it's coming toward you, then basically using the fact that indeed the wavelength has shifted toward the blue end because he's coming toward you, you can easily, the computer inside there will calculate, you know, your speed, if it's going away from you, and so forth. So it's used thousands and probably millions of times.
So it's observable, it's something that can be accepted as
Absolutely.
Definitely a fact.
In fact, that's exactly what astronomers before Hubble had been doing. They put up a spectrometer on the telescope, and they saw that there were some galaxies with shifts of light to the red end of the spectrum, and they clearly said, these must be moving away from us. This is the Doppler effect.
Well, let me ask a question that may display more of my ignorance than I'd like to, but, you know, are there other things that can cause objects to look red? I mean, I see the sun go down, it looks red.
Sure. Well, that is because as the sun goes down, if you're in the desert, of course, or if you're in whatever place that has a lot of dust in the atmosphere, the light coming through, the light from the sun, of course, is a composite of many, many, many wavelengths, okay?
Okay.
Well, when the light comes through and it's near the Earth's surface going down, what happens is that the dust then will preferentially absorb the blue and the green and so forth, and so then what you have left coming through is the red.
Okay. So this is a totally different thing than the redshift.
This is, yeah, the light itself, the spectral lines themselves are not shifted. The same spectral lines remain in the red region and so forth.
Okay,
now,
so we all learn. You and I both learned together on that. Hey, no, but these are the kind of questions that come to my mind. Okay, so this redshift, though, anytime you see it, or anytime you observe, you're going to see that red as something moves further away.
Yes, there is one other explanation which is commonly understood, actually experimentally determined, and that is gravity itself. If you're up in a satellite and light then comes down to where you are, it turns out that there is what we call a gravitational shift of the spectral lines. If indeed light from a distant object coming toward us, just that is up in a satellite, it would actually have the spectral line shifted toward the blue. However, if it's actually rotating, then there's what we call a second-order Doppler effect, and it shifts it to the red. But basically, for our discussion here today, gravity will also shift light either to the red or to the blue end.
Depending on which way it's going.
That's right. Because the Earth itself has what we call a gravitational field. You know that. We're sitting here today. We're not floating in space. And so, indeed, light then that is going through a gravitational field from a higher to a lower potential will have it shifted. Now, the shift, however, is very, very, very small here on Earth. And you have to have special equipment, special experiments in order to see that. But for all practical purposes, when indeed the initial results of Hubble were being published and discovered, there was only one known effect that indeed could explain this redshift, and that was indeed the Doppler effect. And so, as we look at then Hubble's experimental data, you can see that the redshift of the galaxy in the vertical line, the distance of the galaxy from the Earth, horizontal line, and we have then the Earth there at the lower left-hand point, galaxy 1, 2, 3, 4, 5, and we can see that the actual line itself, the lines themselves are going from white to yellow and more yellow and orange and then red. Okay, so what was Hubble's reaction to all of that? Well, the simple, obvious reaction should have been that indeed his result was a monumental discovery, presented astronomers and cosmologists with a huge dilemma because they were accustomed to interpreting the galactic redshifts according to the Doppler principle. Well, okay, let's put that in, the Doppler principle now. Let's substitute then the increasing velocity of the redshift on the left-hand axis there, the vertical axis. So instead of redshift, it is now velocity as well as redshift. The distance from the Earth is the same. Now remember that prior to this time, astronomers had seen some galaxies that were basically shifted toward the red. Okay?
They'd seen that, they observed that through telescopes or whatever.
That's correct. But now one of the things that Hubble did prior to his discovery of the redshift, the relationship itself, in using the 100-inch telescope, the largest one of that day, astronomers did not even know that there existed what we call galaxies, these galaxies that we see so easily.
They couldn't see them.
The telescopes were of such a nature they could not resolve whether the specks of light that they saw were really another island universe, so to speak. But now Hubble, with this new telescope, focused on these more distant galaxies, and he found, we won't go into the details, he found proof that indeed there are other galaxies like ours, the Milky Way. And this resolved a huge controversy in astronomy. Until that particular time, it had always been up in the air. Are we living, within a single galaxy, and are these objects, distant objects? Everything within our galaxy, stars or whatever. So he resolved that, and he got a very, very, high acclaim for this discovery. And so when he turned his attention then to the universe, in other words, using the 100-inch now to measure the redshifts, he came up with this fact that indeed, remember also that for 1,000 or more years, 2,000, whatever, astronomers had always felt that indeed the universe was static, immovable, the bowl of light. They would see the stars, and they didn't seem to move. Okay. And so as a result of that, everyone believed we were living in what is called a static universe.
And Hubble his discoveries just blew that out of the water.
Well, we can see from the slide here.
Galaxy 1, 2, 3, 4, all the way, he thought, he documented or proved why there was more than just one.
Well,
and the shift also showed that there was movement.
Well, if we interpret it that way, it would have shown there was movement. Okay, now, if indeed he had only looked in a single direction, and his early observations, he didn't have a long observing time, if indeed it was found, other astronomers jumped in, other telescopes were devised, manufactured, other astronomers looked at the universe, if it was found that Hubble was only seeing this unusual redshift relation in one direction, people would have said, well, this is very, very unusual in itself. But what they found, of course, is no matter which way you turn the telescope, you're always getting this same redshift relation. So all of a sudden then it became apparent, first of all, that there was order to the universe. It was known, of course, there was order to the planetary
Any way
system.
you look, it's going to look the same, and it's going to document that it's ordered the same way.
Order.
Okay.
And so, as a result of that, this new order, you know, this is a schematic, this is a graphic that simply shows that indeed, the farther the galaxy is away from Earth, the redder it becomes. And the redder the galaxy, the faster it's moving away from the Earth. You can clearly see the movement here, so to speak, graphically, and you get the idea very clearly that you're looking at something, we're near, or at, the center of this vast distribution of galaxies.
Well, let me ask you a question on that point, because as I've listened to the presentation and thought about it, a question came to my mind. That's true when we're sitting here or when Hubble was doing his thing here, but let's say we could transport him and take him 1,000,000 miles away. Would he still see a redshift going every way from his new location?
Well, now that was something that really came into focus as Hubble and others were actually beginning to try to devise an explanation for what they're seeing.
You mean my question, they considered that question?
Absolutely.
Okay.
Absolutely.
Okay. I feel, I guess, okay about that. Well, what did they find?
All right.
Or what did they, I mean, there's no way he could go 1,000,000 miles away.
That's true.
So, I mean.
Well, we can see from this schematic right here that he obviously realized if he used the Doppler interpretation,
right,
that indeed, you know, he would seem to be at the center. Now, your question, which they very quickly, well, I say in a year or so, they really had their wheels turning, figuring, what in the world can we do? Why? You see, one of the principles of science is, if you find something new, what you try to do is use the simplest explanation you can find and generally is true. It's called Occam's razor. All right, so what does Hubble do? He doesn't like that idea. And in his book, The Observational Basis of Cosmology, 1937, he says the following. The assumption of uniformity has much to be said in its favor. If the distribution, talking about the galactic distribution, were not uniform, it would increase with distance or decrease. But we would not expect to find a distribution in which the density increases with distance, symmetrically in all directions. Such a condition would imply that we occupy a unique position in the universe, analogous in a sense to the ancient conception of a
central Earth. Okay.
Now, in the Dark Ages, what entity promoted?
The church.
The church.
The church said we're the center and the world's flat.
In other words, that's well, once they found this out, their Earth being flat went by the wayside, of course.
Right.
But the fact of the matter is...
so he's trying to stay away from that because it's associated with what's considered a prehistoric or something that's been relegated to the dustbin, a center to the universe.
This hypothesis cannot be disproved. That is, the possibility of the center. But it is unwelcome and would be accepted only as a last resort in order to save the phenomenon. In other words, if we have to use that in order to explain what we've seen, we'll resort to it. Therefore, we disregard this possibility and consider the alternative, namely a distribution which thins out with distance. Now, remember, in him saying that, that was the time in which there were only a few observations, and he was making comments about what he presumed to be the distribution and so forth. The main thing that we're getting at here is that Hubble is saying this idea of a center is just, unwelcome, for sure. Now let's look what else he has to say from the same book. To this principle has been added another proposition that all observers, regardless of their location, will see the same general picture of the universe.
So now, that's my point, no matter where they would be, whatever position.
They liked what you said.
They liked what I said.
That's right. If you'd been back in that time, they would
well,
have welcomed you.
I wasn't agreeing. I said, what would happen if you took them 1,000,000 miles away? I was asking what would happen. Would you see the same thing?
I know. Well, they have a very good reason for wanting that. Exactly.
Okay. All right.
That all observers, regardless of their location, will see the same general picture of the universe. The second principle. Now, what principle is he talking about?
That idea that they'd see the same thing.
That's right. Now, he's calling it a principle.
And it's not a principle.
What is it?
An assumption.
Assumption only. It's a sheer assumption. He admits it.
Okay.
Nevertheless, it leads to a rather remarkable consequence, for it demands that if we see the nebula all receding from our position in space, in other words, he's now saying some way, somehow, we're going to get them all receding, okay? then every other observer, no matter where he may be located, will see this nebula all receding from his position. However, the assumption is adopted. Why are they adopting this assumption? There must be no favored location in the universe.
In other words, no
No
center.
center.
Okay.
No boundary. All must see the universe alike. They're decreeing, Hubble and the astronomers of that day were decreeing that, you know, if you go from here to the vast reaches of the universe, take your telescope, what are you going to see?
Same thing, he said.
Same thing. In order to ensure this situation, the cosmologist postulates spatial entropy and spatial homogeneity, which is his way of stating the universe must be pretty much alike everywhere in all directions. That's the fundamental premise upon which all the Big Bang hangs. Assumption. Now, you remember the one that we read earlier at the very beginning? Weinberg is saying one dark cloud hangs over the standard model of the Big Bang. Cosmological principle. He's admitting that indeed, you know, we really don't know for sure.
So what you're saying with this is that the Big Bang assumption that you could go 1,000,000 miles away, which was my original question, is just that, an assumption. But Hubble's initial reaction to what he was seeing was, it looks like we might be at the center of things.
Got it.
Okay, and he didn't like that.
He didn't like it. Didn't want it. Not only Hubble, but Hubble was not in a vacuum. He happened to be the leading astronomer of the day because, you know, he had previously discovered there were galaxies.
Now let me ask you this question. Since we can't really transport ourselves 1,000,000 miles away, there's really no way to test that out.
Well, most people thought that was true. But the fact of the matter is, there is a way. We'll get to that.
Okay.
Continue. Yeah, it's most important that we understand, indeed, there is a way to test that in the here and now.
Okay.
All right, let's continue. First of all, we have to understand that why couldn't Hubble incorporate this idea of everywhere in the universe being the same and use the Doppler interpretation? Well, it's right here in our graphics. Indeed, you know, you have an observer here on Earth, and he sees those arrows, of course, represent galaxies moving away, and the length of the arrow represents the Hubble relation. The greater the distance, the greater the velocity. And then, suppose, you know, there's another
That's
observer.
the guy 1,000,000 miles away now. He's looking.
Let's assume he's at 10 billion light years away.
All right.
10 billion light. He's at the edge of the universe as we see it today. And he looks out, and he just happens to be looking in the direction of us back here, okay? Now, we've decided that the universe looks like there are redshifts, for sure, even out to his position 10 billion light years away.
But when he looks back...
When he looks back, because Hubble and others say that, indeed, he's got to what? See the same thing.
So he would see a redshift moving this way, they say.
Well, he would see... No, he would see...
From his center.
No, he would see, look at it. He would see galaxies moving away from him.
Okay.
Right, that's what he's got to be able to see if he's going to see the same thing, right?
Right.
But now, what are we going to do about the galaxies that we saw moving away from us that are going toward him?
So how does he answer that? That's a big dilemma.
That shows, that's proof, absolutely proof, that you cannot accept the idea that indeed everything is moving away from everything else and all the universe is the same, and use the Doppler principle. You have to invent something new. That is the dilemma they found themselves in. They had to invent something new in order to explain why, if you're at distant reaches of the universe, why you would only see redshifts and not redshifts and blue shifts if you just accept the normal Doppler effect. Big, big, big question.
Big problem. So, I mean, simply put, let's see if this analogy works. You got one guy in the middle of the blackness of night. He's shining a flashlight that way, and the light's going away from him. And he says, I wonder if it probably is the same everywhere. But then you drop somebody as far away as you can, they shine a light, and they both see the light shining at each other. It's a problem.
That's right.
Okay, all right.
On the assumption, that is, under the assumption that indeed the Doppler effect is the reason for the redshift.
Okay.
All right, so they say we don't like, and Hubble and others said, oh, wait a minute, we don't like this idea because, you know, that's an assumption that we see we're at the middle of some distribution. The other guy's got to be at the middle of another distribution. Still, you got to have center. So we want now, in order to get rid of a single center, It's okay now. They want to have multiple centers no matter where you are in the universe. We want to get rid of the single center. That's the purpose of their ideas. That's the purpose of their plans. That's the purpose of everything, to get rid of a single unique center. And so they said, how can we do this? Well, now this was all happening in the early, before Hubble actually made a discovery, 1922, 1924, and also 1927. Back in 1917, Einstein had developed what he called the field equations of general relativity. Okay? He solved the field equations for one solution. That one solution was, in essence, formatted according to, pardon me, what it meant was that the universe that we have was basically in agreement with the static solution of the universe. Well, Einstein thought that was all great, and in fact he was thinking static universe, and so forth. However, in 1922 and 1924, a Russian scientist, Alexander Friedman, took hold of Einstein's equations, and he said, you know, there really is another solution to the field equations here. It's a solution that involves time. Einstein's initial solution of the field equations only involved gravity. But now we've got some gravity and space, but no change in space volumes. Anyway, Friedman and then another person, Georges Lemaitre, a Catholic priest, in 1927 solved the field equations the same way that Friedman had done, and they both ended up with the idea, well, you know, if we use the idea that there's a time element involved in the solution of the field equations, we'll get a different solution, and that different solution tells us now that space itself will have the ability to actually expand with time. Aha. So back in 31 now, this is several years after both Friedman and Lemaitre had made their discoveries, there was a scientist, physicist, astrophysicist in England, Arthur Eddington, very, very, very famous, well known. And he was wondering, how can we actually put all this together and find a solution here to get rid of he also didn't want the center. Well, no one in astronomy wanted the center, the unique center. And they heard about then, Lemaitre told him about this expanding space-time solution of the field equations, and immediately Eddington got his original paper and published it over there in a well-known British journal. Up until that time, it wasn't well known. And make a long story short, the idea was simply as follows, as we can see on this graphic. The Big Bang, I labeled it Big Bang science fiction about the redshift. Okay. Because here we have, first of all, the idea that instead of the universe being a static universe and volumes and so forth not changing in time, all of a sudden we've got the solution of the field equations that says, in theory, that space itself can expand. Take a box of a certain volume. Yesterday, supposedly, it was smaller. The day before that, even smaller, volume-wise. Or tomorrow, it's going to be larger. And so that was one thing they did. First of all, to assume that the universe, you know, was governed by this other solution of the field equations. Why were they doing this? Ultimately, they wanted to get rid of the unique center.
Idea of a center that came from the logical conclusion of the Doppler effect.
That's right.
Okay.
And so that wasn't enough, though, just to say that space itself is expanding. That enabled them, you know, someone said, well, wait a minute, maybe there's a beginning. And the beginning is, well, maybe everything was very, very small to begin with. And that appealed to the Belgian priest, Georges Lemaitre, because he said, well, maybe that was the finger of God. God touched the universe and just everything went from there. And so that was the initial reaction of, you know, of those people who believed in the Bible or God, saying, you know, well, here we've got the ideal thing. We can marry, you know, this new idea with a new with an interpretation of the Bible, you know, that we'll get our cards together here and so forth. New ideas, new theory, but we're going to put it in the framework of still believing in the Bible. Now they were still faced with something else, because the light was shifted to the red end of the spectrum. And they couldn't use the Doppler effect because that would be a huge contradiction. So now they're going to say that when space itself expands, guess what? Wavelengths expand. Wavelengths of light. The whole idea was, as you can see from those schematics, box, small box, the wavelength, very, very short. Next box.
Wavelengths get bigger, and then they get larger.
And it gets redder. Big, big, big thought here. And so they said, let's pursue this. The top up there would be a circle, and then you can see the little sine waves going around and around and around, as if, you know, the light were going around the universe. And then the circle expands, representing expansion of space, and the wavelength gets larger. And guess what, though? Remember we talked about non-conservation of energy? That's where the non-conservation of energy comes in, because the energy of light is inversely proportional to the wavelength. So if you have something with a small wavelength, it starts out with a higher energy. Something with a much, much longer wavelength, you've lost energy.
And this would be opposite that law of conservation.
Well, that's what Harrison was talking about. Non-conservation of energy. You know what? It's hardly ever mentioned. Book after book after book in cosmology.
They don't bring up this problem.
I want to tell you, and we'll talk about this a little bit more in a little while. David and I have written a report that's published on what is called the Archive, in which we showed demands a non-conservation of energy loss equal to a gargantuan 30 million times the mass of the visible universe.
So it's impossible.
We put it out on the Archive. It's available to scientists all over the world since 1998. And no one is basically, thus far, contesting what we're saying. The fact of the matter is, that's a prediction of the theory. And a lot of people, like Harrison, will admit, but they have never put that calculation in any cosmology book or any report that we've been able to find. It wasn't ever published until David and I did so in 1998. So
that's the third or fourth major problem we're seeing here.
Yes. Now, interestingly, as a sidelight here, when I was in graduate school, University of Florida, I was taking a course in cosmology about the Big Bang. And I was absorbing it all. The professor got on the topic, wavelength expansion of the Big Bang. And I can remember, he started on the left-hand side of the room. And the blackboard was probably 30 or 40 feet long. It was a big room. And so he said, what we're going to do here is show you how the Big Bang explains the redshift relationship of Ebb and Hubble. So he put it over here and he wrote the symbol for lambda, and he wrote, basically what we just saw here, small wavelength. And then he started walking across the room, and he'd get bigger and bigger and bigger. Then he ended up on the other side of the room, 30 or 40 feet away, and it was significantly larger in wavelength. Okay? And I was listening, absorbing everything, but then it occurred to me.
What about conservation?
I said, wait a minute. I asked the question. I raised my hand and asked the question. I said, what's going on? Because here you've got an energy of the photon, a certain amount, but if the wavelength is increasing over here at the end of the universe or wherever it goes from galaxy to galaxy, it's lost energy. I said, where did the energy go? Well, he walked back over on the left-hand side of the room and started walking back across the room until he got to the other side again. And he looked at the class and he said, I don't know. I don't know. And so after class, the other members of the class came up to me and they said, well, you raised an interesting question. I said, this is really strange. But I guess everybody knows what they're talking about. It's got to be true. Now, that happened when I was absorbing Big Bang cosmology.
And you saw the flaw already then. And you didn't know that you had seen a flaw. You thought maybe this guy doesn't know an explanation for it.
Yeah, I just sort of like, it's a theory. It's explaining everything in the world, so it's got to be true. Who am I, a graduate student, to think that, I've raised a question that would be of any significance?
Right.
But anyway, it did stay in my mind.
I can tell that it did.
And so here we have, again, Edwin Harrison's book, and this is what he's talking about. Science clings tenaciously to the concepts of conservation, and again, it's good in everything except cosmology, but the very fact of the matter is, if Big Bang cosmology is the reason and the origin of the universe and the explanation for its development, see, that means we've got to be a part of the universe, and so therefore non-conservation of energy has got to apply to us. Big contradiction.
Big contradiction. So then what was the next step?
Just in case that someone has a question and thinking that Hubble was the only one that thought about the center of the universe. You're familiar, of course, everyone's familiar with Stephen Hawking and his famous book, Brief History of Time from the Big Bang to Black Holes. Okay? Well, let's look carefully at what Stephen Hawking has to say in his book, page 42. Quoting, at first sight, all this evidence that the universe looks the same whichever direction we look in seems to suggest there is something special about our place in the universe. In particular, how about that? It might seem that if we observe all other galaxies to be moving away from us, then we must be at the center of the universe.
Mm.
There is, however, an alternate explanation.
He's
The universe,
sighing a sigh of relief. Okay.
the universe, now notice what he says, might look the same, whichever direction, as seen from any other galaxy too.
Might. That's a very key word, isn't it?
The very fact of the matter, that's why Steven Weinberg says, dark cloud hanging over the standard model. This, as we have seen, was Friedman's second assumption. Remember a few minutes ago I mentioned...
It's not a principle, it's an assumption.
That Alexander Friedman, you know, discovered supposedly this other solution, and there's really an assumption. We have no... Listen to this.
We have no...
Go ahead and read it.
We have no scientific evidence for or against this assumption. We believe it only on the grounds of modesty.
Can you believe that?
So he's admitting just what you're saying is the problem. Stephen Hawking, he's probably the most well-known
Scientist in the world.
Scientist, astrophysicist
In the world.
in the world, and he's saying big problems, it's an assumption, and we're only doing it because we're being modest.
Now, let's explore that a little bit more.
What does he mean by
Why
being
is
modest?
being modest? Well, the fact of the matter is, if you just read on his book, obviously what he is saying is that, you know, if you don't believe that, then we're either at the center or very, very close to the center of the universe.
Yeah.
What are we in this galaxy? See, he's an atheist, agnostic.
Right.
He doesn't have anything to do with God. In fact, if you read about him, you'll find that indeed his wife was a Christian, and now I can't vouch that this is still the case, very, very conservative Christian, and Stephen Hawking and all of his talking and work and everything got to the point where she said he's almost thinking like he's God. And so my understanding was several years ago there had to be a separation. She just couldn't take it. Anyway, this fellow is so opposed.
And he's admitting, though, in that statement, he's showing actually your whole argument in a very short paragraph. And if he had taken a different position, his book would not be called A Brief History of Time. He would have to be doing a lot of explaining as well.
Well, yes.
Because he'd be standing up and actually standing on the scientific evidence that you've presented and saying, we've got to look at another option.
Actually, it would be much stronger than that, because you see, when he says, as you say, why is he saying this on grounds of modesty? Well, see, because as we mentioned before, for an astronomer, astrophysicist, you know, who, remember, doesn't really have any connection with God whatsoever, he doesn't want a connection with God. He doesn't want the Bible. He doesn't want the moral premises of the Ten Commandments to be meaningful, but he knows if there is a center of the universe, there is a God, and indeed there's only one religion that really focuses on God being the creator. So he says modesty basically is saying, listen, fellas, you know, if it's not modesty, we're there. And we don't want it. You're right. Stephen Hawking is basically admitting what we're saying here today in a very, very concise way.
Yes, he is. That's fascinating.
Most people don't know this.
That's
they read
fascinating.
The book, they read the book and they don't understand how strong the evidence is for the other side. Here we are with good old Hubble Ultra Deep Field, thousands and thousands of
galaxies again, that's the same
you know,
picture.
at the far reaches of the universe, and some of those we remember have been analyzed for their redshift, and indeed the little green circles there are picking out the ones in Hubble Ultra Deep Field, where indeed in the middle of those circles the light was shifted so far to the red that instead of seeing, you know, a bright dot, you were seeing red dots. And so there on the right side of the panel you can see the larger circles. You may not be able to see it clearly, but each one of those larger circles has a red dot in it.
I see that, yeah.
And so indeed, basically, it's essentially true. Observationally, the greater the distance, the greater the redshift, even to the uttermost limits of the universe.
But let me just be clear on this. All evidence points on the face of talking about Hawking, talking about Hubble, talking about these others that have admitted it. They're saying, hey, look, if we just take the Doppler effect, we're in the center. We've got to come up with something that doesn't put us in the center, because we don't want to not be able to get our PhDs or go to school sort of like you described at the beginning. So we got to come up with something else. They've come up with that kind of thing. But now, if you really look closely, they recognize that it's breaking all of those different principles like conservation and all those different things. It's not making sense together, and yet that's really given no real play in their books and what they're writing and what they teach their students.
And the reason is because they have adopted the idea that observations plus observations plus observations can be fitted into that framework, just like Ptolemaic astronomy. They just got all sorts of planetary observations can be put into the Ptolemaic astronomical viewpoint, so people thought it has to be true. And so what happened is Big Bang cosmologists failed, the greatest blunder in all the history of science. They never really then tested the fundamental assumption of space-time expansion in the here and now.
And have you done that?